what I mean by a propagation complete formula. And then I will want to talk briefly about an implicational structure of these formulas that allow us to use a learning algorithm for learning implicational systems to compile to a propagation complete formula. So in knowledge compilation, we are usually interested in translating some kind of knowledge representation from a source language to a target compilation language, where the goal is to have the target language in such a way that we can answer queries using some reasoning algorithm. And the reasoning algorithm should be efficient, so the answering queries should be efficient after the translation. But the compilation time can take, or the compilation can take some non-trivial amount of time. But the idea is that we will compile once and then reason many times. So for purpose of this talk, I will consider knowledge represented using propositional logic. So basically, we are representing a Boolean function, which is a function on an inputs which are 0, 1, and the result is again 0, 1. So one like natural language for propositional logic, I would say, is a formula in conjunctive normal form, which is a conjunction of clauses. Each clause is a disjunction of literals, where a literal is either a variable or a negation or of a variable. The advantage of this language is that it's really expressive. It's kind of natural. If you want to encode something into propositional logic, then actually anything can be translated into a conjunctive normal form by using standard tools. But the disadvantage is that even to check consistency of such formula is a hard problem. We have to use a SAT solver, which can take a long time depending on how hard is the input. So we wouldn't say that this is a suitable target compilation language. And basically, we are interested in like improving this language with some further properties so that we can reason more efficiently over the representation. Okay, so our reasoning technique will be unit resolution and unit propagation, which you may be already familiar with. But the unit resolution simply takes a clause which is in form C or L, and then a single literal non-L, and it derives the clause C. So in this case, for example, and unit propagation for us is just iterated unit resolution rule. I will use this V-1 notation to denote the fact that a clause can be derived by this unit propagation. Mostly I will be interested only in deriving literals. So in this case, for example, we can derive non-x1 from the formula phi because it's already a unit clause in the formula. Then we can derive non-x4 as well. And we can derive x2 because we already know the non-x1. So from the second clause, from the third clause, we can derive non-x3. And now the fourth clause became empty. So we have the contradiction. Yeah, so this is how we use unit propagation, and based on this, we can define propagation complete formula as a formula which has this property that if a literal is implied by a formula together with a partial assignment, which is basically a set of literals to us only, or a consistent set of literals, then it can be derived by unit propagation. But of course, it's also possible that the formula is inconsistent with the partial assignment. In this case, it implies every literal, but we cannot expect that every literal would be derived. So we only require that either contradiction or the literal is derived. So for example, if we look at this formula here, it's not propagation complete, because if we set x4 to false, then it's implied, x1 is implied, but we cannot derive this using unit propagation. So if I write falsify x4, then yeah, so then the only way how to satisfy this is to have x1, right? Okay, so it's because if we falsify x1, on the other hand, then we derive x2 and non-x3, and we derive x4. But if we add this clause, which represents this implication, x4 or x1, then it becomes propagation complete. And we call these clauses empowering. So an empowering clause is such that it's implied by the formula. Basically, this is the first property. And there's a little in this clause such that if we remove it from the clause and set all the other littles to false in the formula, then we don't derive a contradiction, but we also, well, the contradiction is not implied, but we also don't derive the little else. So if you look at the first and third condition, it means that the little is implied, but it's not derived. And we can actually show that was in the original paper introduced by which introduced propagation complete formulas, that we can use this notion to characterize propagation complete formulas, because formula is propagation complete if it has no empowering implicate. It's also of interest that if you take a formula run as subsolver, then all the clauses that are learned during the work of the subsolver are empowering in this sense. So the notion of empowerment comes actually from satisfiability solving. All right. So the propagation complete formulas, if we consider them as a target compilation language, which was the case already from the original paper from 2012, then we can answer consistency-related queries just by unit propagation. So, like consistency with a partial assignment, causal entailment, model enumeration, because we have also conditioning, sentential. If then these can be done by unit propagation. If we don't have any auxiliary variables, then we also can answer sentential entailment, validity, and implicant checking. But usually, if we, for example, use the formula to encode some constraint, then we usually use auxiliary variables, and we don't have these properties. But also from the perspective of constraint programming, if we have a constraint encoded using propagation complete formula, then basically we get generalized R consistency maintained by just unit propagation. So our goal here is to take any formula and compile it into a propagation complete formula. So that's what we want to solve. So the first approach that was considered already in the paper that introduced the propagation complete formula by Bordeaux and Marquez Silva is the following. So we said that a formula is propagation complete if it doesn't admit an empowering implicate. So just keep adding the empowering implicates until it becomes propagation complete, right? Eventually, if we take all implicates of the formula or on prime implicates, then we get a propagation complete formula. So the process stops at some point with the propagation complete formula. There is one obstacle that we need to be able to find an empowering implicate, right? So that's the incremental approach. But we want to take a slightly different approach, which is like more complicated, and that relies on the fact that actually both unit propagation and the modeling relation have like implicational structure. So what I mean by this is that we can define a unit propagation closure of a formula, and for a partial assignment with respect to a formula as follows. That will be all the littles that can be derived by unit propagation from the partial assignment. The set is contradictory if actually contradiction would be derived, and that's enough for usually. In this case, we don't require that all the littles are derived, but only that the set contains a set of contradictory literals. So in this case, for example, if you look at this formula here, if we take partial assignment just A, then we don't derive anything but this A, right? If we consider non-B, then we can derive A, but nothing else. And if we consider B and C, then we can derive B, non-B, C, non-C, and A. And for example, C, non-C means that this set is contradictory because actually this would derive a contradiction. So this would be an inconsistent partial assignment. Right. So this would be a unit propagation closure, and similarly, we can define a sort of a semantic closure. So we can say we can have a set of literals that are implied by the partial assignment, right? So this is this SF alpha, S phi alpha is all the literals that are implied by the partial assignment. Now the difference is that in this case, if the formula is inconsistent with the partial assignment, that actually all literals are implied, right? So it consists of all literals if the formula is inconsistent. So for example, for this formula, which is propagation complete, so we have that for these A and non-B partial assignments, we get the same closure because we derive the same literals as they are implied. But for the inconsistent partial assignment BC, we have this difference that in case of unit propagation, we don't have non-A. It's not in the formula, we cannot derive it. But in case of semantic closure, even non-A is implied, even if it's not in the formula, right? Because everything is implied by a contradiction. So, so we can use these closures to characterize propagation complete formulas the following way. That the formula is propagation complete if for every set of literals such that we cannot derive a contradiction by unit propagation for this set of literals, the unit propagation and the semantic closure might be same. So whatever is implied, we can derive by unit propagation. Right? So one inclusion is always true. The unit propagation closure is always a subset of the semantic closure, but the opposite inequality is true only for propagation complete formulas. So what's interesting is that these are really closure operators. So they are extensive, monotone, and idempotent, which means that they define implicational systems. Right. So what I mean by this is the following. So if you look at the unit propagation and the clause that is used in unit propagation, it actually can be interpreted as implications, right? So in this case, for example, the clause C that has 3 literals corresponds to 3 implications that corresponds to 3 possible ways in which you can use them in unit propagation. So you have that if it's X or non-Y or Z, then we can, if we set non-X and Y, then we derive Z, right? And the same for the 3 other cases. If we take all these implications for all the clauses in the formula, then we get an implicational system. So it's just a conjunction of these implications. Implicational system on literals. And this implicational system defines the closure operator, right? U phi. What we want to do actually is that we want to learn the implication system that corresponds to a propagation complete formula. And because the system is also defined by a semantical closure operator, it's actually same for all propagation complete formulas. So if you have 2 propagation complete formulas that are equivalent, then they define the same, the closure operator, the semantic closure operator is the same, and therefore also the unit propagation closure operator. So in this case, we want to simply learn the implicational system that is associated with the semantic closure operator. And that's nice because for learning implicational systems, there is an algorithm. Actually, there's an algorithm that learns the system using so-called equivalence and closure queries. It actually follows from much older algorithm that uses equivalence and membership queries. This is sort of improved version. So the algorithm is polynomial in there's a polynomial number of these queries, which is a very nice feature. But of course, the queries themselves, in our case, are hard problems, both of them. So for an equivalence query, what it means is that we want to check if the implicational system we already considered, which is associated with a conjunctive normal form, is already equivalent to the one we want to learn, the one associated with semantical closure. And that's a co-NP complete problem. That's the same as checking if the formula is propagation complete. So that this actually follows from an early result, but we provide a specific encoding. The original paper didn't include any encoding to SAT, but it just showed that it belongs to co-NP. So for us, more important from the co-NP completers is not that it's hard, but that's pretty obvious, but that it belongs to co-NP. So we can use a SAT solver to solve this task. A closure query is maybe a bit simpler, although still hard. In a closure query, we want to compute all the literals implied by a partial assignment. So that's computing the semantic closure of a partial assignment. And that again can be used, can be solved using a SAT solver. Actually, this relates to finding backbones formula. So we can use a SAT solver again. And actually, it turns out that for the equivalence queries, these are much harder than the closure queries in this case, because the encoding we provide is polynomial size, but it's one is quadratic and one is like n times log n. So it's certainly bigger than the original formula. All right, so just to say more about what we mean by a negative example. So a negative example in this case, or an equivalence query means trying to find a negative example. A negative example to us is a set of literals, which is like not inconsistent with bi-unit propagation, but the unit propagation closure of this set of literals is not equal to the semantic closure. So we have some literal that is implied but not derived by unit propagation. So actually we can use various sources to find these negative examples. The first, of course, are the clauses from the input CNF. So the algorithm starts with an empty implicational system. Okay. Then we can use random queries, but most important is the satisfiability-based equivalence query. So the learning algorithm uses the following approach. It starts with an empty implicational system, ask an equivalence query. If a negative example is found, it tries to use it for refinement. If refinement is successful, then asks again an equivalence query. Otherwise, the implication is added to the formula psi. Right. So, and when this process ends, we have a propagation complete formula. So this is like the overall structure of the approach we took. So I will skip this part about the SAT-based equivalence query. So this would be the encoding is described in the paper. It's quite non-trivial. So just to give some impressions, we also made some experiment with this approach to compare with the incremental approach, mostly for comparing the number of equivalence queries, basically. So in first set of test cases, we used random instances, and then we use selected instances from the compiled project, which is present on this web page. The reason is for using random instances is because because the equivalence query is quite hard. It's not usable on big formulas, and the formulas from this set are quite big. So on some, if we are lucky, then on some of these formulas we succeeded, but actually most of the formulas in here are quite out of reach. So that's why we also considered random formulas, but to introduce some structure, we used a modularity-based generator that uses some introduces some community structure. So these are the results on the random formulas. So we can see that the learning approach, that are the lines L, the LR are the lines where we also use random equivalence queries that also help. Then the learning approach certainly decreases much the number of the empowering implicants that needed to be found by the SAT. The equivalence query is by far the most expensive part of the algorithm. And it also influences the time. For the benchmark formulas, these are the ones we were able to solve. Well, actually, there's like several more of them, but these are like the selected ones. Again, you can see that the learning approach is much more successful in all the cases. Yes, probably. So this is maybe interesting because most of the formulas have lots of backbone litters. So this third column is the number of the variables in the formula after we remove the backbones. So it's interesting for this line because here we actually incremental approach didn't succeed at all, and the result had like 16,000 clauses. Anyway, so should finish. So I will just mention that there are some, of course, other popular languages in knowledge compilation as target languages like DNNF formulas. These are there are good compilers to DNNF formulas like C2D or D4, and they also include order decision diagrams, for example. So I just want to point out that although they offer like the same queries and answering the same queries, then in some cases the propagation complete formula we found are much smaller than the DNNF you could construct using, say, D4. So using this approach, we get much smaller structure with the same set of queries we can answer. And also CNF can be much easier embedded into some other, some bigger problem instance. And I would also mention that there are some other approaches to this problem. These are kind of brute force enumerate all partial assignments, so they are usable only to a very small number of variables. Okay, so to conclude my talk, I will mention that the process still has two big limitations. So the first one is that the output formula can be actually much bigger than the input one, right? In reverse case, it can be exponential. There are some examples of formulas where it's really necessary to add exponential number of clauses to make it propagation complete. And the second case is that the checking propagation completeness is really hard. Right? So we try to construct an efficient encoding, but still it's much harder than reasoning just with the original formula. For the future research, we would like to consider adding some auxiliary variables in the process because we don't add them, and the auxiliary variables can make the formula much smaller. So, yeah. So, okay.
Questions? I was just wondering what's the succinctness compared to the other AC languages?
Yeah, so it depends on if you consider also auxiliary variables, existentially quantified auxiliary variables, then propagation complete formulas are strictly more succinct than DNNFs. And you can translate a DNNF into a propagation complete encoding using auxiliary variables. If you do not consider auxiliary variables, then I think they are incomparable.
But you're not doing auxiliary.
No, in here we don't consider auxiliary variables.
But in the experiments, you didn't show auxiliary variables.
No, there were no. That's because okay. So one way how you can do it is if you want to introduce in auxiliary variables, you can construct a DNNF, and then you can translate this into a propagation complete encoding. But that the number of these variables can be really huge. So we want to go sort of bottom up, that we start with no auxiliary variables, and maybe in future research we would like to devise some technique like bounded variable addition or something like that to make the formula smaller.
And then in the experiments, right, you show compilation size, but compilation time?
Yeah. So here we have time. Yeah.
But compared to like before.
So
no, sorry, in the next one, right?
Yeah. So this one.
Yeah.
So D4 is much faster.
But how much faster is that?
Okay, so for C714 it was like okay, so it was like 3 minutes, and D4 finishes like 1 second. So it's really much faster. And for C211 it was even the difference is even bigger. And the hardest part actually, that one of the like sometimes quite non-trivial amount of the time is just checking at the end that the formula is really propagation complete. So that's the last check takes quite a lot of time of the compilation. So it's not like the compilation, it's just checking that the compilation finished. So that's so if you stop early, you can get something like an approximation propagation complete formulas that might be enough in some cases.